Okay, let's. Before I start, I think I did it last week, but I don't recall mentioning it here. So there were a bunch of questions. There are a lot of questions regarding the definition of regular sets. So here, things like you wrote in the exercises. I was told that. So there was this exercise whether all finite sets are regular. You were supposed to prove that they are. And some people wrote, okay, so empty set is not regular, and so on and so forth. So I just redefined, so the definition was not clear enough, what is meant under star, what is meant under other things. So I made the definition clear cut. So if you want to learn about regular sets, especially for the midterm, then I advise you to just go back to the slides where I introduced. So I just made slight modifications. So now you see that star here. So these are the modifications I made. So language star will always include an epsilon, no matter what. So then in the definition of regular languages, so let's go here. We will say instead of starting with epsilon, we start with an empty set like this, and we say that the empty language is regular. And pay attention that if we know here, maybe here, that if your language is regular, the star of that language is regular also. So in particular, this would mean that if you notice, the star of an empty language is epsilon, because by the definition of star here, star is what? All strings from your language, basically, all length of your strings. So if your language is empty, this is again empty. There are no strings in there, so you cannot construct strings from empty language. But you take a union with epsilon. So epsilon star of an empty language will be epsilon. You can see it here. So epsilon will automatically be regular. So one language that contains one string, namely the empty string, will also be regular, but the empty language is different. Empty language would be, if you think about DFAs, the empty language would be a DFA where you do not have accepting states. And something that has an accepting state as a start state, but then it transitions to something else, and it never accepts, that will accept epsilon. So different DFAs, except maybe it's a good exercise to construct a DFA that accepts epsilon, and that is different from the DFA that accepts an empty language. So just take a look once again about look at the definitions of a regular language if you were confused about that. Now we defined that the empty language is regular, which is different than the language of that contains epsilon, and then everything else stays the same. And then we will have all finite languages will be regular, and so on and so forth. I did the modification, I think maybe 2 weeks ago or 1 week, I don't remember, and so I just wanted to warn you that this modification happened. So if you downloaded slides beforehand, re-download this particular slide once again. So okay, so this is for regular languages that we just turn off now. And now we continue with our lectures, and we were almost done with the slides about Chomsky hierarchy. So I think we were basically here. Yes. So we were proving, let me not go full screen as of now. So we're proving the pumping lemma for context-free languages, and I looked at the recording and we spent like 20 minutes explaining this even before we started to prove. So I will just go on a limb. So I'm just going to assume that you looked at it, and I'm going to start with a proof this time. So maybe actually call the OneNote and prove it there. So here is the definition. Well, here is the statement of the lemma that if you have a context-free grammar G, for any context-free grammar G, there is a number n0 such that for every word in this language which is longer than this number, so longer than n0, so this is supposed to be big W here, so it's longer than n0, it can be decomposed in 5 parts, U, V, W, X, Y. This is big W, small w, such that V and X are not empty, otherwise you would get a trivial statement, and you can pump on V and X, right? And so let's look at, so here is actually we have from last lecture, we'll try to prove things here, I guess. So might as well use the same. So if we erase all of this, we can use the same pictures. Blah, blah, blah. So here are the pictures, and the idea is that if I have my grammar, if I had my grammar, I have my production rules, right? So B follows something, maybe X. So I have production rules like this in my context-free grammar, and I choose my number. I think in your slides, your number is denoted by S. So S is so I look at all the productions, they are finite, and I look at the longest right-hand side of my production. This is S. I call this guy S, and then we observe that if your word is in your grammar, so it's in L of G, then it has a derivation tree. If your word has a derivation tree, this means that, so now I look at derivation trees. So I start somewhere, and I know that, so if I start at the root, right, I don't know. So this is small s here, by the way. So let's start at the start symbol, maybe big S. So at most it can have S small many descendants, because if I want to create a derivation tree, I have to use one of the production rules on one first step, and the longest production, the right-hand side of the longest production is S, so it has at most S children. And then in the worst case, well, worst or best case or whatever scenario, each one of them again will have S children. Like this. So the tree of height 2 will have S squared children at most. And then we proceed and see that tree of height H will have S small to the power H many children at most. And this goes vice versa. And you know that you go all the way down here, and here you have your word derived. And if your word has length, let's say SH plus 1, then the derivation tree of this word has to be at least H high. That is the point. So now what I do is I have to pick my pumping number, right? This N0, so I go back here to my proof. So I pick my N0 to be S to the power hashtag N. So hashtag N is a number of non-terminals I have. These are my inner nodes. So let's say I have 3,000 non-terminals. I will take S to the power of 3,000. S is also a fixed number. So this is a fixed number. And what I'm claiming, so it's S to the power like this. So as many non-terminals I have, I take that power. And if my word is longer than this, somehow, then the derivation tree has to be longer than, so the height of the derivation tree of any derivation tree of W has to be the height of, let's say, derivation of W has to be bigger than hashtag N. So let's take this plus 1 or whatever, just for simplicity, or this plus 1. Let's take for my pumping length something like this, so we're on the safe side. And if your W is longer than this, then this is longer than this. The height of the derivation tree is number of all terminals plus 1. Now I look at the longest path. So this is let's say the derivation tree of my W, and I know the height is bigger than this. Right? That means if I look at the longest possible path here, this will have length hashtag as many non-terminals I have plus 1, the longest path. And then, okay, this guy is at the leaf I have a non-terminal. So that means I have at least this many, well, actually there are n plus 2, but whatever. So at least this many non-terminals on this path. And if there are at least this many non-terminals, then one of them has to repeat. So this is the length, if you have height n plus 1, you have n plus 2 nodes, right? In the path of the length n plus 1, you have n plus 2 nodes. So I have hashtag n plus 2 nodes. I'm overcrowding so I have that many nodes. One of them is a terminal, namely the leaf. All others are non-terminals. So that means, let me go back here so we can see. That means I have, what is this? That means I have hashtag n+1 non-terminals on this path. That means at least one of them repeats, because there are only n many non-terminals, and if I take n+1 non-terms, that one of them has to repeat by the pigeonhole argument, and then we do this. We explain this extensively, that okay, this guy repeats, so I can excise this portion of the tree and glue it together here. You will get repetition of v's and y's, and if you completely remove and glue the lower occurrence of r to the upper occurrence of r, you will remove v and y completely. And you can do it as many times as you like. You can continue doing this like this, and you will get repetitions of v's. So this says that any derivation tree which is taller than hashtag n+1 will have a repeating, somewhere in there, you will have a repeating non-terminal, and then you can take the lower non-terminal and glue it to the upper non-terminal, and you will again get a derivation tree, a valid derivation tree, because all rules will be kept. And you can also take the top one and glue it to the bottom one, and you will get a valid derivation tree for another word. And then we discussed how these words are created. So x is whatever is the lower r derives, vxy is whatever upper r derives, and then the whole word is uvxyz. There is a caveat here, though, that I have to prove, namely that v and x are not epsilon. And I will leave it as an exercise. I will put it in the exercise sheet, and this is an important exercise. This will ensure that you understand this proof, and this will also ensure that you, and do this proof and modify the argument so that you can prove this as well. That will make sure that you understand the argument, and the hint is that you have to consider not just any derivation tree of W, but a derivation tree that is minimal in some respect in order to prove this. Because there can be many derivation trees, and you just consider one of them which is minimal, and you use that to prove it. Your book proves it, by the way, but I will encourage you this time to not look inside the book, not look into your book, but rather prove it yourself, and then if you cannot do it, then you can go ahead and look in there. So this actually proves the pumping lemma for context-free languages. And there is an exercise then that this particular language, now we take three things, a to the power n, b to the power n, and c to the power n, where n is a natural number, is not context-free. Recall that we had this guy, which was not regular, but it turns out now if you take three things that repeat, A, B, B, C, C, and so on, then this will not be context-free. And in order to prove it, you have to use pumping lemma for context-free languages, like decompose this in 5 parts, like what was it? U, V, W, X, Y. So you decompose every word in 5 parts. You can take words of arbitrary length. This goes the same, but now you have many different cases you have to look at, because you can pump on W, V, I, Y. You can pump, and you can see that in every way you go, you break down the structure. It's maybe hard. There are more cases here than in just this one, but it's provable. So we just found out another observation on Chomsky hierarchy, that we had regular languages here, and we knew something was out here, namely this AN, BN guy. And now, then we knew that this was context-free, this guy, because it had a grammar which was context-free, we saw it. And now we saw that there is something out here also. So these things are really disjoint, that's what I'm claiming. So regular languages are not the same as context-free, because there is a language that is context-free and not regular, but every regular language is of course context-free. And now we found out there is something that is not context-free. So we are really classifying the hierarchy. So it really is a hierarchy. It's not just equality. This is what I'm specifying. And you can actually prove that this thing is context sensitive though. You know, we had the regular language, we had this language A and B, and we proved it's not regular. Then we gave you a grammar, so it's context free. And now I can give you a grammar, namely this one, that generates this language. And so here is the grammar. I'm not gonna go into this. So this, I can just specifically give you a grammar. It's of course context sensitive because it satisfies all the rules of a context sensitive grammar. And you can go through an exercise. We'll put this in the exercise that actually this grammar generates this language. So your non-terminals, you have 1, 2, 3, 4, 5 non-terminals, 3 terminals, and these are the production rules. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 production rules. And if you do this, this is a context-sensitive grammar on the notes, but you have to prove that these productions really generate this language, so you will know that this language is context-sensitive. So we know that, so again, to draw this, we will know that we have regular languages, then we have context-free languages. There is something here, we know this. Now there is context-sensitive languages here, and we know that there is something here. Of course, we know that there is something here as well. There are any finite languages here. There's something here, there's something here. So this is really hierarchy. And then there's like the type 0 guys here. But we do not know whether there is something here as of yet. Maybe every type 0 is actually context sensitive. We don't know this. The final differentiation that will complete Chomsky hierarchy is not there yet. And so this is like a computing with grammar if you actually want to prove it. And this is an interesting exercise. And then there's a caveat that finding a type 0 language is not context sensitive is a different world, which will take us to Turing machines. Okay, now what we're going to do for this coming hours is construct a machine. So let me go back here. But before we do that, we'll maybe do the Chomsky normal form. Yeah, let's do Chomsky normal form first. So I turn this off. I'll save it. Okay. So yeah, so let's jump right in. So we are going to define a Chomsky normal form and what it means. So for this, again, let's just recall what the context-free grammar was. So it's 4 things: non-terminals, terminals, production rules, and start symbol. Well, production rules are what? It's 2 things, basically. You have a non-terminal on the left, in case of context-free grammar, just 1 non-terminal, and a string of non-terminals and terminals on the right. Basically, this was it. And I redefine it, I make it more comfortable. You can see a star here. I also allow things like this. I will allow, before I didn't allow things like this at all. Then I said that I only allow this from the start symbol, that if I want to produce an epsilon, I can only have start symbol that produces an epsilon. But now I'm just going to allow it that any non-terminal can produce a epsilon. And I'm going to show you that this is the same thing. So some authors in some textbooks define context-free grammar this way to begin with, but let's just do it. So you have a grammar like this. The only restriction I really have is on the left side, I just have single non-terminal, and the right-hand side can also have just empty string like this. So these things are allowed. So what is a Chomsky normal form? A context-free grammar is in a Chomsky normal form if these are all the productions I have. I have only three kinds of productions. First kind is that I have 1 non-terminal on the left and 2 non-terminals on the right. So I'm banning all longer strings. So all my productions are like this. A follows B, C. Either this, or I'm also allowing 1 non-terminal on the left and single terminal on the right. And then only the start symbol can produce epsilon. So this is much more restrictive than this here. This allows any length on the right, bunch of different things. And I'm saying that I can always bring my grammar, change it so that it only has these 3 types of rules, and it will produce the same language as the grammar I started with. This is the point. არა, ეს მარტო 2 სიგრძისებს არა, ჩვენ მეტი შეიძლებოდა აქეთ. ხო. We even restricted much more. Only these 2 things are allowed. Before, I allowed the longest strings on the right side, but I did have only this before as well. But now I'm saying only start symbol produces epsilon, but I'm restricting even farther. I'm saying that only rules are of these 2 kinds. Non-terminal, single terminal, just one, B is just a single terminal, it's not a string. And A, B, C, where B and C are single non-terminals. So let's just go through this exercise. And you have seen it somewhere, and the question is where, but I don't know where have you seen this. Maybe in OS or something. Chomsky normal, I mean, it maybe was not named Chomsky normal form, but you've seen context-free grammars in this form before, somewhere. So you might as well recall it. Anyway, the lemma is that every context-free grammar with this definition here, meaning that it's very general, I'm allowing every non-terminal to produce epsilon, not the old definition, even the more general one, can be transformed into context-free grammar G prime, which is in a Chomsky normal form, which only has these rules. I'm just going to go through how to do it. First of all, what I do first is the same thing we did before, is that I eliminate start symbol on the right. So if there's a start symbol that appears on the right, so I start with a grammar which is in this form, and I'm changing it to a grammar which is in this form. First thing I will do, if there's a start symbol on the right, I will create a new start symbol S prime, and I will add a new rule, S prime implies S. So now my new start symbol is S prime, and it's no longer on the right side. The right side just has this symbol S, which is no longer a start symbol. Okay, we did this before, nothing special. Okay, now what I want to do, I want to make all my production shorter so that it only has 2 letters maximum on the right side. How? So let's say I have a production like this, which has more than 2 symbols. So I have a production N implies A1 up to AS, and S is longer than 2. Maybe I can make it larger like this. Yeah. So I have a production that has N here, and it says something longer than 2. How will I make it shorter? It's very easy. I will create new non-terminals X and replace, so I will create a new non-terminal named X, and I will replace N by, before I had this, now I go to S minus 2, and these last 2 letters are replaced by X, and now I will introduce new rule that X implies AS minus 1 AS. So I erased last 2 letters here, and I created a new rule, X implies this last 2 letters, and I wrote X here. So how much shorter is this side now? That's down. But I will keep on doing it. So now I will do the same thing again, introduce new non-terminal again, until I come down to 2. So I'm introducing new letters, so X, Y, Z, and never run out of letters, and I'm introducing new rules like this. Each new rule only has length 2 on the right. This is Chomsky normal form. The new rules do not violate it, and the old rules are now thrown away. So repeat until all right-hand sides have length 2 or 1. Because if my right-hand side had length 1 to begin with, I didn't do anything. Okay? What next? So now if I do this, all my productions are shorter now. They're at most 2. So the first rule maybe is almost satisfied. So now what I want to do is I want to eliminate epsilon rules. This needs more thinking. So what I'm doing is this. So now I have a bunch of new guys, namely non-terminals that produce epsilon, and I want to remove them. But how do I remove them? Because they do in fact build some productions in my, they build some derivations in my grammar. So what I do is, now I have finite number of non-terminals, right, that are different from my start symbol, my new start symbol S prime. So I look at all my non-terminals and I number them. Let's say they go from 1 to m. So n1, n2, and m. So they're finite, so I number them. And I run a for loop. What is my for loop? From 1 to m, I do the following. First I would look, so I start at 1, so first I look at n1. Is there a rule that n1 implies epsilon? If there is such rule, I drop this rule. But it's not okay to just drop it, because maybe n1 is on the right-hand side of some rule, and then before I was able to replace it by epsilon, but now I'm not able to replace it by epsilon if I do not have this rule anymore. So what I do is, first I drop this rule, and for each rule with ni on the right side, I add a rule where each occurrence of ni is dropped. Namely, if I had a rule like this, so remember all rules are now length 2. I did this before, so I have no longer, so all my right-hand sides are length 2. So if ni appears on the right-hand side, it's either this, or this, or this. So if I have a rule like this, or like this, I will add a new rule that n directly derives x. Because before I was able to replace ni with epsilon, now I dropped it, so I add this rule. Okay? And for this thing here, and if k is bigger than I is my index that I'm running my for loop on. So in case I is equal 1, so for all bigger k's bigger than I, nk derives ni will be replaced by this one. So even though I remove this rule, I might have created one again, but somehow this k, not somehow, but this will be taken care of on the next iteration of the loops. Because I'm only replacing bigger k's always. When my loop catches up, it will drop this rule at some point. So when my loop goes through, I will have no longer such rules, and all the rules when the right-hand sides were like this, they will be taken care of. By the way, this is a usual exercise, also on the midterms as well. By the way, you know that in the exercises you get some exercises from midterms too. And so to give, it might be that you're given a grammar and you're supposed to turn it into a Chomsky normal form, and you're supposed to go through this. So first you reduce everything by 2 by introducing new non-terminals, and then drop these rules, but if some things occur on the right, you have to add the additional rules like this. But now I did this, but I have to prove something, that when I'm doing this, I'm not done yet. I still have to do some other things, but this is the only non-trivial part of doing this. So, okay, I made this guy shorter, this is clear. But when I drop these things, I have to make sure that the new grammars I'm creating on every iteration of the loop, during I equals 1, I dropped some rules, introduced some new rules. In I2, I dropped some rules, introduced some new rules. So I have to prove that on every iteration, the language that my grammar produces is not changed. So this is what lemma 2 says. This is not completely trivial, is that if gi be the grammar after pass of I of the loop, so let's say g7 is when you iterate this loop up to 7, then the language that the original grammar generated is the same as g7. That means that when you finish the loops and all your rules are eliminated, epsilon rules are eliminated, you still end up with the same language. So this is an induction on I. So when I equals 0 is by definition, your g0 is the same. No loop run has occurred yet, so it's the same language basically. Maybe it's, you still did this shortening of the things, but this is trivial somehow that the language stays the same. But anyway, so g equals g0 is trivial. For now, let's say, so let's look more closely what happens when you go from I minus 1 to I. So let's assume that you did I minus 1 iterations of your loop and your language stays the same, and you did the ith iteration of the loop. And let's say your word was in the original grammar. So by induction hypothesis, there is a derivation tree of W in Gi-1, because induction hypothesis says that Gi-1 is the same as Lg, so W is also in Lgi-1, because I assume this is true for I-1, and it has a derivation tree. So if it has a derivation tree in Gi-1, that means it doesn't use the rules Nk implies epsilon for k less than epsilon, because I removed all of them. So all the rules like Nk implies epsilon are already removed in I-1 for k less than I. So it uses no rules like this. And all the productions Ni implies epsilon in Lgi are already replaced by these rules here. So this word will also belong to Lgi-1. So this is a small... It's not completely trivial, but it's easy somehow. You have to say something like this. And the other way is easier. If your word is in Lg minus Gi, how do I prove that it's Lg? So I replace in a derivation tree of W in Gi each use of the new production rule that I introduced, namely this one, by the original one that happened before. So I replace this guy by this guy. So I go back somehow. And W will be in Lgi-1, which is the same as Lg by induction hypothesis. So this is one of the examples where the proof is easy, but if you do not follow it, you should go back to it and look at it yourself. One cannot make it clearer somehow. Okay, so at least you understand how, okay, we made everything shorter, and then we removed epsilon rules. So there was a question before that, okay, in some books define context-free grammars as allowing every non-terminal to produce epsilon. Now you know that if it's produced, you can drop those rules, introduce some new rules, and get a grammar that doesn't allow this. But anyways, I still have to take care of rules like this. So if I have two non-terminals, A implies B, I didn't allow this in Chomsky normal form. In Chomsky normal form, I only have A implies BC when B and C are two things, and A implies B where B is a terminal. So you cannot have X implies Y, and both of them being non-terminal. So if you have a rule like this, A implies B with both of them being non-terminal, I just remove this rule, and so I will drop A implies B, and for all productions that I have B implies U, I will add A implies U. So it's easy, right? If you had A implies B and B implies U, you remove A implies B and add A implies U. So like a transitive thing. So you will repeat this until no chain rules between non-terminals. So these rules will also be dropped. And this is, so what to do about the rules A implies BC, A implies BC, like C being terminal, or A implies BC. This is an exercise. So let me ask you a question. How would you get rid of this rule for, let's say, A implies... So you want either a non-terminal, so you want something like this. So let's say you want to turn this into something like A implies BC. Well, not the same C, maybe it's different. So maybe A implies XY. How would you turn this rule into A implies XY? Exactly. You add something like this, and then you add something like this, right? This is what you say. So you can do this kind. So also with two non-terminals, you can do A implies BC, then B implies B small, and C implies C small. So you have to do this. These are like the tricky exercises. The only non-trivial part is actually removing epsilon rules, because when you're removing them, the right hand, you're also messing with the right-hand sides of other rules, and you have to run a loop there. Okay, so this proves that we can bring every context-free grammar to Chomsky normal form, and what it's actually a fruitful lemma that follows, which you're not going to prove. It uses dynamic programming, which we did not have time to get to. It's called Younger's algorithm. Is that if you have a context-free language L, there is an algorithm which decides whether your word is in L in O(n) squared time. Not squared, O(n) cubed time. So let me enlarge this, and let me just say a couple words. So what does it mean to decide whether word is in there? So remember, we talked about this extensively, that languages are basically problems. So, for example, if you have your language, by the way, there was an exercise to prove that language of all prime numbers is not regular. And you had to prove this. This was also on the midterm, but it's on the exercise worksheet. So we were giving this language as an example. So let's give it again. So if you have a language that consists of prime numbers, basically. So there you had a unary, so you had as many ones as the prime number or whatever. So it's a unary language. But so you have a language of prime numbers. What does it mean to decide whether your string is in there or not? It's basically asking whether this is a prime number or not. This is the question you're asking. And deciding on n cubed time means that if you're writing your prime number in unary language, meaning that 5, zoom out. So I'm meaning that 5 is just 1, 2, 3, 4, 5 like this. And 7 is 1, 2, 3, 4, 5, 6, 7. Is this 7, 1, 2, 3, 4? This is 8. So it should be 1, 2, 3, 4, 5, 6, 7. So this is unary. And this will be the size of this will be your n. So in this case, n equals 7. That means if I input a prime number of size in unary of, I don't know, 3, or 5, then 5 cubed will be as many, O(n) cubed will be the number of steps you will need to tell me if your number is prime or not. So if your language is context-free, if we assume that the language of prime numbers is context-free, then we can do it n cubed time. And if we can do this, everything is broken. Our banks, everything, because they all use cryptography on prime numbers. And if you can decide whether something is prime in cubed time, this would be. So, but if your language is context-free, meaning if your problem is easy enough, it's not as easy as regular problems, regular languages, but in some sense it's context-free, then there exists an algorithm that for every context-free language decides it's at n cubed time. And you might think, how would one do this? How would one do this is maybe the first approach would be, okay, if your word is in your language, it has a derivation tree. Now, derivation trees are particularly easy. They're basically binary trees at most because they're in Chomsky normal form. Everything can have derivation 2 at most. And then every node can have 2 sons in a Chomsky normal form. So maybe I can go through all possible trees somehow and find if my word has a derivation. So this is just the ideas that one might pursue, and how would one use that this guy is in Chomsky normal form. So to make your algorithms faster somehow. You do not have to go through all possible sons, rather only 2. Anyways, so we're not going to do this proof. What time is it? Okay, we can still have 7 minutes. And rather, we will go to... Okay, by the way, are there any questions on this? I'm going very fast. I did a bunch of things already. So let's record again. So now what we're trying to do, maybe I go to the drawing board. So let's see what we did. So we had Chomsky hierarchy. So let's call it type 0 here. These are type 0. And then we had regular languages. Then we had context-free. I know I can draw this because there is something here. I know there is something here. I know. And then we had context-sensitive languages. And I know that there is something here. So this is this guy and this guy. So this, by the way, let's make it, this is A and B and guy. And this is A and B and C and guy, like this. And this here is maybe just A, just one letter A. So this thing occurs, and then what we did is so people in linguistics, maybe not linguistics, and some mathematicians were developing this theory. But there were computer scientists parallel to that who were also developing computation theory, and they were doing the same thing with machines. So these two people got reconciled pretty early on, and we know that there are machines that are equivalent to, you can describe these languages by machines. Instead of saying that regular language is something generated by regular expressions, context-free language is something generated by context-free grammar, you can say the same thing with machines, and we know that regular languages are exactly specified by DFAs, which it turns out is the same as NFAs. Now what we're going to do, we're going to construct a machine here, and that will be a non-deterministic push-down automaton. So this will be like a DFA, but it has an extra property that it has a stack to the side. So it has this memory of, you know, we covered stacks and queues and stuff like this. So it has also an available stack to the side. And so this will be, and it will be a non-deterministic machine. And I will warn you right now that this is not the same as deterministic pushdown automaton. The fact that this happened here was actually, I wouldn't call it a miracle, but it's a special feature that DFAs and NFAs are the same. It turns out that non-deterministic pushdown automaton and deterministic pushdown automaton will not be the same. By deterministic, I mean that for every configuration, there is just exactly one next configuration. There is one thing it can do, but NPDA has many things it can do. Right? So let's describe what is NPDA. Or maybe just describe it here, and then we give a definition in the next hour. So let me draw this. So my NPDA looks like this. So maybe use a thicker thing. So again, you have a tape. So this is your tape that you're reading your word onto. So let's take my alphabet for simplicity to be 0 and 1. So it's basically B again. So my word is something like this. I don't know. So this is my input. It goes on like this. And then there is your machine again. Your machine, which is in state Z, and it's reading, let's say it's reading this input. This is your DFA. How your DFA works, it reads the input, and according to delta, it moves right and changes again. Right? This would be DFA. And the only difference here is that I have this thing called stack that actually maybe like right like this. So it continues down. So if I draw like this, this also has some symbols. So let's, I don't know what to call it, gamma 1, gamma 2, gamma 3. And this guy also reads this. So now when you're in state Z and read 0, what you can do is you can, if you were DFA, you just change the state and move right. But in this case, you can change the state, move right or do not move, and you can also update your gamma. So you have an additional thing that you can change. An additional thing you can, maybe you add something to gamma or remove something from gamma. So push or pop. So think of the gamma as this way. Think of gamma as a stack. Basically, it is a stack. So stack is you have an axis, so you only see the top. Right? If this is stack, you notice that you only see the top here. Everything else is kind of hidden. So Z can only act on gamma 1 in some sense. It can remove it, and then it sees gamma 2, remove it, it sees gamma 3. It's pushed up somehow. Right? It can remove it all the way up, or it can add things only on top. It cannot add things at the bottom. So somehow, usually they give the definition of like, if it's a table and it's like a canteen or cafeteria in Germany, they don't, or they used to do it in the Soviet Union as well. So, you know, when you have plates and it's spring-loaded on the bottom and you just see the top plate, when you take the plate, it pushes up. So your machine is working and it has also this stack of plates that you only see the top plate here, which is spring-loaded on the bottom, and when somebody for lunch takes this plate, the bottom plates are pushed up, unless the tray is empty. This can also become empty at some point. So initially how your machine would start, initially how, let me end the sentence, initially how your machine would start, it will have an empty stack, and it will start at the beginning of the word, but instead of reading the word and changing state, it can also save something in the stack. So stacks acts as a memory, basically an infinite memory that you can save. And we'll see why this is very strong in a minute. Okay, we are talking about non-deterministic pushdown automaton. There's a deterministic pushdown automaton as well. It's not the same, it's weaker actually. And there are languages called deterministic context-free languages. And those are the ones recognized by deterministic pushdown, but we're not going to cover them. We would just do not have enough time. So there's another layer in the Chomsky hierarchy, which is smaller than context-free and bigger than regular. But those we do not cover. Let me just quickly say, so we just intuitively defined what this guy is. It's drawn here. So this is my determinist NPDA. And what I'm claiming now is that this should, even though I have not defined what it is, what it means to accept, I'm just saying that intuitively, this is already stronger than DFA. Why? Consider this language again. So we consider this language, so let's make green. So 0 to the power n, 1 to the power n, this n is natural number. So we know this is not regular. We know you cannot accept this with a DFA. So you cannot build a DFA. I will just tell you right away how to build so intuitively how to build the pushdown automata for this. So that means something here is written like this. So let's say 0, 0, 0, 0, 1, 1, 1, and let's say 1. So this should be accepted. How will this machine work? It will start here. So it will start here. And if it sees 0, so I will also tell you what these things are. So this is called gamma. So gamma are things I can write on the tape. Let's say this is the same. Let's say it's again 0 and 1. So things I can write on the tape is 0 and 1 again. So let's actually differentiate. Let's make it black and white. Just to show that this can be different. When it sees 0, if I see 0, so initially I start with an empty, so this thing is empty initially. So it's like this, just one thing, and it's completely empty. If I see 0, I put down black, let's say. Then I move right, I see 0, I put down black again. I see 0, I put down black again. When I see 1, I will start removing black. So I do not need white, by the way. I just need one symbol. Black. So I keep on putting blacks when I see zeros. And when I go to 1, when I see 1, I change my state. So I go to a different state. So initially I'm pushing state. And then I go to when I see 1. So when I see 1, I go to popping state. So I have push state and pop state. So I'm pushing blacks, and then I see 1, I start popping blacks. And when I go here, in the end, my stack will be empty. If my string consists of as many zeros, as many ones, as there are ones, then my stack will be empty, and I will accept. So my accepting state is, okay, see if your string is finished, whatever, and if your stack is empty, then accept. Otherwise, reject, because if there is a 0 again somewhere here, maybe in red, if there is a 0 here, I will push black plate, push, 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 pop one plate, then I push again, pop, pop, and there will be one plate left, or 2 plates left. So I will not accept.
With that logic, will 0, 1, 0, 1 will not be accepted because the stack will be empty, but the grammar is...
Good, actually. What I should do, if when I see 0, I go to a pushing state. Then I see 1, I go to a popping state. But if I'm in a popping state and I see 0, I should reject. So there's some modification you should do, right? So this is just intuitively speaking, because I haven't defined what this thing is, what is computation, what it means to accept, but you can kind of see intuitively that this already grants you some powers. Even though I have to, yes, if you have 0, 1, 0, 1, I have to, when I see 0, 1 again, I have to go to a different state which rejects right away. But okay, let's see. So now that we know that this thing is more powerful because it has the stack, let's actually define what this thing is. And remember that this thing is non-deterministic, so it will do weird things. Stack, yeah, right. This is... No, states are many states. However, I can do two things with the stack, either push or pop. So I can be in many different states. Oh, you mean the example. In the example, I should have pushing state and popping state, maybe something else, the reject state or something like this. Because in the example, but generally you can have many states. However, you can only perform two things. Let's actually define it and you'll see how this actually works. So my pushdown automaton, non-deterministic, NPDA, will be 1, 2, 3, 4, 5, 6 things. Set of states. So it's a finite set of states. Then I have finite input alphabet, meaning, so things I can read on the tape. And by, I recall, but this is sigma, but by sigma epsilon, I denote things I can read plus epsilon. This is sigma, just a notation. So just ignore this for a moment, what does sigma do? So what is gamma? Gamma is a stack alphabet, the things I can write on my stack. So gamma epsilon denotes things I can write on my stack plus the epsilon. And then now I will have, by the way, in your textbooks, there are many different versions of this definition, but they all are the same. Again, it just, you can always go from one definition to another one by just, so if you have two definitions, what does it mean that two definitions are the same in this context? That, let's say I gave you a definition of a pushdown automaton this way and somebody gives you a different way. This usually means that if I have a machine that works with this definition, right, and it accepts some languages, this machine also accepts the same languages. So basically they're the same. So in terms of language acceptance, they are the same. This is what I mean by same. So okay, gamma is things I can write here on the, so this is the same picture as we drew. And now I have two push down actions. So, well, there are actually more than two. So PA will denote, maybe let me zoom in. So what is PA? PA is either pop, so these are things I can do, or they're for each gamma, epsilon, meaning for each letter in my gamma and also epsilon, I can push gamma. That means, so if there are, so in my example I had plate black name, so let's say there are many different things I can push there. So let's say it's numbers 0, 1, 2, 3, 4. So let's say there are 4 things I can push here. So I will be able to remove, like from the stack, the same way. So you can remove from the stack or push 0, push 1, push 3, or push 4. So there are 5 things you can push, but only 1 remove somehow. And pushing epsilon means doing nothing. So what I can do is in state Z, I can read the letter and push epsilon. That basically means I did not change my stack. I can also do this. So I have, so if my gamma contains 5 things I can write, then PA will contain 6 plus 1, 7 things I can do. I can remove 5 things I can push, and I can also push epsilon. Okay? And what is my most important non-deterministic transition function? This is, so it looks at the state, it looks at what is written on your alphabet, also it can read epsilon, which is written everywhere. So okay, let me actually give you intuition on this. So Let's ignore epsilon for a moment. So what it does is, in some state z, it reads the letter, it looks at the stack, and it performs the action. These are all possible subsets. So what this basically means, I have to zoom out. So let me write here. So if I have delta, let's say in state z, my symbol that I'm reading is A, and my symbol is gamma 1. We called it gamma, and it's also called gamma here. So this is, so top of my stack is gamma 1. This is A is the symbol on a thing, and I'm in state Z. So this is a set again. It's a subset of state and a push down action. So this will contain things like maybe Z5 pop. It will also maybe contain, this is just an example, Z17 push, I don't know, gamma 3. And maybe it also contains the third one, Z4 push epsilon. What this means that if I'm in state Z, let me get the laser. So if I'm in state Z, there is A written here, and gamma 1 is the top symbol here. I can do three things. Because they're non-deterministic, I can do any one of them. I can go to Z5 and remove gamma 1. That is this one. I can go to Z17 and add gamma 3 on top. Or I can go to Z4 and basically do nothing with the stack. This is basically what it is. But now, what this definition allows is for me to have epsilon here as well. So let's try to think what can. Let's try to think what can. So what can this guy mean? The epsilon gamma 1, let's say. What can this mean? So epsilon is an empty. So it's written everywhere basically. So if you're reading a tape A, B, C, D. There's an epsilon between A and B. You can think of it this way. So it can always read epsilon. So what this means that if it's in state Z, let's call this guy. Let's say it's a specific state Z3. So if it's in state Z3, without even looking at the tape, basically this is what epsilon means, because epsilon is everywhere, so might as well not look. Without looking at the tape, if gamma 1 is here, I can do whatever this is. So let's say this is only single guy, there's only single choice. I go to state Z4 and I pop. So this means that if I'm state Z3 without looking at the tape, and there's gamma 1 here, I can go to Z4 and pop gamma 1. So at some point, without looking at the tape, I can do actions. Right? And it might be that there are many different choices. Hence, there's an epsilon here, and there's an epsilon. Epsilon here, by the way, what does this mean? Maybe Z4 epsilon epsilon. Let's say this is Z17 push gamma 4, and there's some other things. I don't know what. What does this mean? This means that if I'm in state Z4 without looking at the tape or without looking at the pushdown symbol, I'm not looking at any of them, I can go to state Z17 and push gamma 4. Because epsilon is written everywhere on the tape, and it's also written on top always. So if there's some plate here, there's nothing on top of the plate as well. So you can take nothing somehow. This is what it means. So by the way, there's different definitions of what, so in Hopcroft and Ullmann is defined differently. You can push many things at the same time. In your Sipser's book, it's defined differently, but they all hide something that you cannot do this, which is apparent here. So we stated out that you cannot remove something when you're ignoring gamma. That means that what is delta Z A epsilon? That means that you're in state Z, you're reading A, and you're ignoring the pushdown symbol. So you're not looking at the pushdown symbol. This is what delta Z A epsilon means. So akroikos A. That means that what can you do when you're ignoring the stack? This is what this guy describes. In state Z, when you're reading A and ignoring the stack, you can do, and I'm banning that you can pop. Because what this effectively would do intuitively is you can start popping without looking what you're popping somehow, and this completely destroys the structure of your stack. That means you can access any point of your stack by just removing it without reading anything and without looking what you're removing. You don't want to do this. By the way, this also bans that if your stack is empty, you cannot remove anything from the empty stack, because you cannot pop if your guy is empty. If your gamma is empty, the only thing that is there is just an empty string, so you cannot pop from an empty string. So this also bans popping from the empty string, but it additionally bans removing things without looking at gamma. So this is your pushdown automaton. Now we have to describe, or first let's say what do we mean by, how do we start? Yeah, first, we don't say how to accept first. Let's first say how do we start. So initially you start with a start state, Z0. You have to have a start state. See, Z0 is, yeah, by the way, I have a start state, I forgot to say. So I have states, alphabet, tape alphabet, push down alphabet, transition functions, start state, where I start, and accepting states as DFA. What is my initial configuration? I start in a start state. It's W, so configuration is, the word is written. So configuration now contains three things, right? Current state, the word that is remaining, the same way as on the DFA, and also it contains this whole string of your pushdown symbol. So for example, if we go, so let's say this is my tape, and I don't know, this thing is written here, my machine is here in state Z17, and my push down has, I don't know what, A, B, C, like this. Then my configuration would be Z17 1010, there's the remaining word here, and A, B, C. So just the convention, first letter I will write is the one that is on top. I do not write CBA, I write ABC. So I read it from top to bottom. So this is my configuration. This completely should determine what should follow next. And I'm saying that initial configuration is Z0, the whole thing is written, W, and this guy is empty. So initially my stack is empty. I cannot start with, say, filled in stack. So now I'm asking you a question, maybe here in green. So let's just rewrite this. Let's say I'm Z17, 1010, and ABC. This was my configuration. And let's say the next configuration is Z12, I don't know, 010, and BC. So this is not a good question to ask, but anyway, so there may be many different configurations. So now I have to tell you how do I know what the next configuration can be. Remember, in DFA it depended on delta. So the state here in the DFA, so let's call it DFA, you had delta of Z, you would have Z17 and 1. This was what would go here. But now your delta also defines what happens here, right? It should also tell you this. So now what I'm going to do, I'm going to describe this. Maybe it's the best option to actually show you. So what it means to have the next configuration. So let's enlarge it and look at it. Somehow textbooks avoid it, but I don't think there's anything to be avoided. So let's say your configuration is you're in state Z, your word is W, so this is a string, and P is also a string. It's everything that is written on a pushdown symbol. And let's say your next configuration, you went to state Z prime, your word is now W prime, and your P also changed P prime. So when can this happen? This is now I'm going to describe what does it mean to go from what states can I write here. Of course, it depends on your delta function again. And first, I'm claiming that maybe I can actually write pen. It kind of zooms out when I choose pen. But anyways, so let's say my delta ZW1P contains, so this is a set of many different things I can do, contains Z prime and pop. Then what is one of the possible next configurations from ZWP? So my configuration is ZWP. W1 is the first letter of W, right? And let's say this guy is inside here. Then the next configuration I will write for you. What next configuration can be is I can go to state Z prime, right? I can read W1, so I can go to W2, right? So if I'm writing a configuration, so it's W2, W3, and so on. And I can pop, so I can start P2, Pn. See what I did? So if I was in state Z, my word was W, and P was my pushdown string, then the next state, if Z prime pop is in my options, can be I go to state Z prime, I read the first letter, so the letters left are W2 up W3 up to Wn, and I popped the first guy, so it's P2 up to Pn. Yeah. Okay, this is all it says. Now, what if I can push? What if Z prime push gamma is there? What should happen is I should go to, if Z prime push gamma is here, the next state will be Z prime, again W2 something, so this will stay the same, the word is red, but now P1 will actually increase by gamma, so gamma will be concatenated with P. So if pushing gamma is there, I can push something on top. Only difference here and here is that I had tail here and I have gamma here. But now the main caveat is this guy. So let me write this. What does this represent? Delta ZW1 epsilon. Let's say this guy contains Z prime push gamma. So that means that when I'm in state Z and I read the letter W1, I can completely ignore what's on my stack, not look at my stack, and still push gamma. This will give me the same result as if I looked and saw P1 and pushed gamma. So if this thing is either here or here, you will get the same result. Tail of W will be left, and P prime will be P push gamma. Let's try to record this. So look what's going on. When I'm defining my function delta, I'm defining it from Z, here it is the definition. Z, this guy, so let's write it. This guy to the power set, so 2 to the power push down and states, or states push, push down action and states, or states push. So this is Z, right? For every triple, you have to tell me what's happening. So if you tell me what's happening for ZW, you have to tell me what is this, and you also have to tell me what is this. So W1 here, W1, P1. Both of them you have to specify if you're specifying this function. And what I'm claiming now, that you specify this, right? This is some set. And let's say this set contains Z prime push gamma. Then from here you can go here. We just explained if this set contains this specification, that means maybe the easier one is if this guy contains the same thing. If this guy contains this, means that in state Z, when I see W1 and I see P1, I can go to Z prime and push gamma. However, if this guy contains this, I can basically get to the same place exactly, but specifying here from this specification. So when you define your delta, if you include this, I don't know if you included this here or maybe included this there or not, but I will always have an option to go from here to here with this specifications if this guy included either here or here. So this is the way to get from here to here, but there's also another ways to get here to here. Now look what so this one ignored the stack, but what if I ignore what's written up there? So let's say my pop, so if I'm in state Z, I do not look at the word whatsoever, but I only look at the stack. That means I read epsilon up there. If this guy contains pop, that means the word will stay the same. This is very important. So you're not advancing. You can do this. In DFA, you're always advancing, but if you're not reading anything, you're not advancing. So your word stays the same. However, because of popping, you can pop this guy. Unless this guy is completely empty. We bend this. So you can pop without reading the letter, and also you can do the same with pushing. But pushing now also allows to not read the word, not look here, and push. So if you specify this, so when you're writing your program, right, you have to specify what this is. For all triples, you specify. So if you include something here, so this is a set. So let's say you include something here. Z17 push, let's say 0. This is a 6. What this means that when your machine is in state 6, no matter what is written up there and no matter what's happening on the stack, it can always go to Z17 and push 0. If I put epsilon here, what this means that from Z6 you can spontaneously go to state Z17 without changing anything. You could not do this with DFA. This has much more freedom. So this actually specifies what you can do in state Z6 without independent of what's written on the tape and what's on the stack. But we banned that you can pop. Pop cannot happen here. Pop has to always read this, otherwise structure is destroyed. And this is basically it. So this completely described what can the next state be, and it depends on a bunch of deltas, and usually they do not do this in textbooks. Oh, we only have 9 minutes. So let's quickly say what is a computation now, and let's least try to give an example. So a computation now is a sequence of configurations as before, where a start in the beginning, the push down is empty, the word is written completely. This is where you start. And I will say that this computation has to follow the rules that I just stated, that all delta transitions, the possible delta transitions are happening. And I will say that I accept, this is important, if in the end, so I finally reach some configuration here. So this A is a string, B is a string, and Z is my state. I will say that I accepted that in the end, if in the end, my state is an accepting state, which I declared beforehand, this guy is empty, and this guy is empty. Well, this means that I will only accept if I read the whole word and my stack is empty, and my state is accepting. So I'm requiring my stack be empty, the word completely read, and I'm in accepting state. There are different definitions in the textbooks such that they say that I accept if my stack is empty. I do not care about my state. They also say, I accept if I'm in the accepting state and I do not care about my stack. But these things are the same. And this is in your homework. You have to prove that if you have a machine like this, you can transform it to a machine like that, and so on. ანუ მთელი სიტყვა წაკითხულია. ანუ არაფერი აღარ დარჩა. So you cannot accept in the middle without reading the input. This is what it's saying. And LM will be all languages accepted by your machine M. So all strings accepted by your machine M, those strings are in your alphabet sigma. So, and we will want to prove that the strings accepted by your machine, the languages accepted by these machines are context-free. And let me just give you one more example and we conclude with this. We have 7 minutes, so we can do this. Let's look at this weird language. So let's say my strings are zeros and ones. So again, my strings are just zeros and ones, you see. And my language consists of a string and then that string in reverse. So it consists of strings like this. 0, 0, let's say. 0, 1, 1, 0. 0, 0, 1, 1, 0. 0, 1, 1, 0, 0. So you see what I'm doing? So if I have a string W, I have the same string in reverse. So I have, this is W, this is W in reverse, and the same thing here. These are only some strings. For example, this guy, 0, 0, 1, 0, 1, 1, is not there. So this will not be in my language because there is no point when you can reverse it and it's the same. This language is context-free. Why? Because this guy generates it. It's written up here. S, so 0S0, 1S1, and epsilon. Why does this grammar generate this language? How would I generate, let's say, this string? So you're first generating the outer layer. So for example, this guy, you will start with S0S0. Then you will, in the middle, generate 01S10. And then use the epsilon and 0110. So you can clearly see that this, it needs a proof, but you can clearly see that this grammar really generates this language. And this grammar is clearly context-free. It satisfies all the rules of context-free grammar. What is the pushdown automata that accepts it? You cannot build a DFA that accepts it because you kind of do not know. Like if I would do something like this and then like put a hashtag or something and go like 100, then it's much easier because you see a hashtag, you change your state, and somehow you have to memorize what you read and then do it other way around. But now I do not have a hashtag. ხო, ეგ DFA რო არ არის, pumping lemma-ი გამოვა, ხო. რო დაფაფავ აირევა. მაგრამ რა ნახეთ, so let's look at the pushdown automata that accepts it. I have to give you all possible triples, but I won't. All other triples, you can think what can they be, empty sets or whatever. But I will give you. So this is the DFA that accepts it. It has two states, Z and Z prime. And let's say Z is the start state and Z prime is an accepting state. So when I'm in my start state Z and I see 0 written, without looking whatever is happening on my pushdown, I push 0. Then again, I stay in the same state. See, I stay in the same state and I push 0. Again, if I see 1, without looking whatever is on my stack, I push 1. So what's happening is I'm reading 0, 1, and I'm pushing these symbols, zeros and ones, as I read them. And spontaneously now, by a guess or a God's given hand, if I'm in state Z, without looking what's written there, and without consulting my stack, I can go to state Z prime. This is an important point. This will also be used in non-deterministic Turing machines a lot. This is a oracle guess. So I guess that I'm in the middle, but what's really happening is you can think of at any point I can go to Z prime. So, but in the middle I can also go to Z prime and start popping. So if I see zeros on both, I pop. If I see ones on both, I pop. And I, of course, the only possible configuration that will lead me to an accepting state will be this languages here. I know you have questions on this. Let's stop this. Let me stop the